Hello, I welcome you all in this course on steam and gas power systems. Today we will solve problem related with the fuel gas analysis. In this problem, the gravimetric analysis of hydrocarbon fuel indicates 80% of carbon and 14% of hydrogen. Determine the percentage analysis of combustion products by mass and by volume. What is the percentage of mass, percentage by mass, and what is percentage by volume? Is there carbon dioxide and water vapor and maybe carbon monoxide. And when 50% of excess air is supplied for combustion, when 50% excess air is supplied, it is assumed that there is no formation of carbon monoxide, it is only carbon dioxide. So, when the carbon is oxidized to carbon dioxide, C plus O2 is equal to CO2. So, 12 kg of 1 mole means 12 kg of carbon, 1 kilomole, 12 kg of carbon will form 44 kg of carbon dioxide, right. So, from this we have per kg we have 0.86 kg of carbon will form 44 by 12 multiplied by 0.86, and that will give 3.15 kg of carbon dioxide by mass. Regarding hydrogen, H2 plus O2 is equal to H2O, 2 times. So, 4 kg of hydrogen will give 36 kg of water vapor or water. So, 0.14, that is 14%, will give 36 by 4 into 0.14, and that is going to be equal to 1.26 kg of H2O. Now, there is 50% of excess air. We have supplied, first of all we have to find the air, how much air is required, and then we will calculate how much excess, in kgs how much excess air is there. So, total oxygen is required is how much? It is total oxygen required, yes. Now, this is product of combustion. Now, oxygen required. For burning 12 kg of carbon, 32 kg of oxygen is required. So, for burning of 0.86 of carbon, the oxygen required will be 32 by 12 into 0.86. Right? This is for carbon. For hydrogen, similarly, for burning of 4 kg of hydrogen, 32 kg of oxygen is required. So, for 4 kg, 32 kg is required, and for 0.14 kg, 32 by 4 into 0.14. If we take sum of this and this, it comes out to be 3.41 kg of oxygen. This is about don't get confused with the product of combustion. This is product of combustion, and this is oxygen required for burning carbon and hydrogen. Now, this 3.41 has 50% excess air. It means the excess air is 3.41 into 1.5. So, total air is 5 so total air is, this is oxygen, this is oxygen, right. Now, we are using 50% excess air. So, 50% excess oxygen, this is not excess air, this is excess oxygen. So, oxygen is 3.41 into 1.5. This is total oxygen. So, the total oxygen is 5.115 kg. Now, this is the total oxygen supplied. So, total oxygen divided by 0.23 will give you the total air, right. Now, this is total oxygen, and what about excess oxygen. So excess oxygen is 3.41 multiplied by 0.5. Sorry, yes, 3.41 into 0.5, and this will give around 3.41. 1.705. Now the burned gases are also having nitrogen. It is written here, determine the percentage analysis of combustion products by mass and by volume. So the combustion, the nitrogen will also go with the flue gases. In order to find the quantity of nitrogen, how much nitrogen is going with the flue gases. So this is the quantity of oxygen, 5.115, quantity of air divided by 0.23, and amount of nitrogen is multiplied by 0.77. This will give the amount of nitrogen which is coming out to be 16.932 kg. So product of the combustion, we have carbon dioxide 3.15 kg, water 1.26 kg, nitrogen 16.932 kg. Oxygen, how much oxygen? 1.705 kg. This is also going. So this is the nitrogen, amount of nitrogen which is going with the exhaust gases. This is the oxygen going with the exhaust gases, because oxygen is supplied in excess, 50% excess. This is water going with the outgoing gases, and this is the carbon dioxide going with the outgoing gases. So we will make a table. So it is CO2, H2O, nitrogen, oxygen. CO2 is 3.15, hydrogen, this water is 1.26, nitrogen is 16.93, and water is 1.705. It's 93.2. They are all in kgs. Okay, so this is the composition of exhaust gases. So what we have done, we have taken from the composition of carbon and hydrogen, we have calculated how much carbon dioxide and how much water will be produced, how much oxygen will be used for burning the carbon and hydrogen, or oxidizing for hydrogen and carbon, and that oxygen is 50% in excess, because air is 50% excess, so oxygen is also 50% excess. So we have calculated the oxygen, 50% oxygen is going with the flue gases, and with the quantity of oxygen gas, we have found the quantity of nitrogen. Okay. Now after this, what we have to do, determine the percentage analysis of combustion product by mass. So take sum of these. Okay. So sum of all these is 23.047. This is the sum, and then by percentage you can always take 3.15 divided by this. So 3.15 divided by this multiplied by 100. So 3.15 divided by 23.047 multiplied by 100. Accordingly, we will do for this this water, nitrogen and oxygen as well. And the values are, this is 5.47, 73.47, 7.39, and this will be 13.67. Okay. So this is by mass, let us say this is G. Right. Now volume. Now we have to convert mass into the volume. If you remember, if we take 1 kilomole of any gas, it will occupy 22.4 meter cube of volume, or 1 mole will occupy 22.4 liters at NTP. So volume occupied by 1 mole is same for all the gases, right? And how we will get the mole? Mole fraction, just mass divided by the molecular weight, we will get the mole fraction. So molecular weight, let us take Y, is here for CO2 it is 44, this is H2O it is 18, nitrogen 28, oxygen 32. Now here we can take the mole friction. So when we take the mole friction, then G is divided by Y. So let us take G by Y. So mole friction is 0.311, 0.304, 2.624, 0.231. So here we are getting mole friction. Percentage of mole friction will be percentage of volume, because one mole is for all is occupying the same volume. So here again this sigma gy by L is taken, that is 3.47, and again taking percentage, this multiplied by this divided by sigma multiplied by 100. So 0.311 multiplied by 100 divided by 3.47 will give the volumetric concentration of carbon dioxide, that is 8.96. Similarly for water it is 8.76, for nitrogen 75.62, and for oxygen it is coming 6.66. Right? This is how the percentage by mass we can convert into percentage by volume, because this is very important when we will deal with the combustion of the fuel. When the fuel side, unburnt fuel side, it is always in kgs, but when we do the gas analysis, we find composition of the gas, they are given in percentage in volume. So this conversion, so the person who is dealing with the combustion has to be very comfortable with these conversion in from percentage of mass to percentage of volume, and for conversion from percentage of volume to the percentage of mass. Now in this problem it is required to calculate the proportion of heat of fuel carried away by the flue gases for the following data. Coal with calorific value of 30 megajoules per kg. So the calorific value of the coal is 30 megajoules per kg. It has composition carbon 78%, hydrogen 5%, oxygen 8%, sulfur 2%, and it has nitrogen also, which is 2%, remaining is ash. It is burned in a furnace with 50% of excess air. The flue gases leaving the chimney are at 327 degrees centigrade and atmospheric temperature is 15 degrees centigrade. So the temperature of the gases is increased from 15 degrees centigrade to 327 degrees centigrade. Assume perfect combustion, it means all carbon is converted into the carbon dioxide. Specific heat for dry products is 1045, that is carbon dioxide, sulfur dioxide, right. Heat carried away per kg of moisture in the flue gases is 3000 kilojoules per kg. Composition of air is also given here as 23% and 77%. So first of all we will start with the product of combustion. Now the CO2, how much CO2 has been formed? So CO2 is 0.78 multiplied by 44 by 12. As we did earlier, C plus O2 is equal to CO2, this is 12 and this is 44. For burning 12 kg of carbon, we require 44 kg of, we produce 44 kg of carbon dioxide. 32 kg of air is required and 44 kg of carbon dioxide is produced. So for burning 0.78 kg of carbon dioxide, so carbon 0.7.8 kg of carbon, this much carbon dioxide will be produced, and that is equal to 2.86 kg. Similarly for water, for H2O 0.05, that is 5% of hydrogen is there, and water will be produced into multiplied by 9, that is 0.45 kg. Sulfur dioxide, S plus O2 is equal to SO2, 32, and this is 64 and this is 32. So 1 kg, 2 kg of sulfur dioxide is produced with 1 kg of sulfur. So here the sulfur is 0.02 multiplied by 2 is equal to 0.04 kg. So these are the product of combustion. We are burning per kg of fuel. Per kg of fuel is having 0.78 kg of carbon, which is producing this much of carbon dioxide. 5% of hydrogen, which is producing this much of water vapor. Sulfur dioxide 2%, which is producing this much of, sulfur is 2%, which is producing 0.04 kg of sulfur dioxide. Now how much oxygen will be required? Now oxygen required will be oxygen. I'll write here. For carbon 0.78 multiplied by 32 by 12, because oxygen is 32, C plus O2 is equal to CO2. So this is 32 or this is 12. So 32 by 12 multiplied by 0.78 plus 0.05 multiplied by 8, as in the case of hydrogen, H2 plus half O2 is equal to H2O. So 1 kg, so this will require 8 kg of oxygen. Now another is sulfur dioxide, which will take 1 kg of, 0.02 kg of oxygen. So the total oxygen required is 2.5 kg. Here also excess of air is supplied. I mean 50% excess of air is supplied. So oxygen will be there in the combustion products. Nitrogen will also be there in the combustion products. And that nitrogen will also contain nitrogen in the fuel also, that is 2% of the fuel, or 0.0 kg of nitrogen which is already available in the fuel. So that has to be added in that nitrogen. So 50% excess air. So this is air required, 50% excess air. So 50% excess air is 50% excess air, it means 1.5 just a minute, 2.5 kg of oxygen, and oxygen is also available in the fuel also. So actual oxygen is not, outside oxygen is not, oxygen is required 2.5 kg, but oxygen from air supplied is required as 2.5 minus 0.08 is equal to 2.42 kg. This oxygen will come from air. Now 50% of this is actually supplied, so 2.42, and this will be equal to 3.63 kg. Nitrogen, if you want to find nitrogen, how much nitrogen is supplied, it is 3.63 divided by 0.23 multiplied by 0.77. This will give how much nitrogen is supplied, that is coming out 12.152 kg. Nitrogen is coming from here also, so that will also be added here. The 0.02 kg will also be added here, and that will be the final amount of nitrogen in the flue gases. Now we have all the products of combustion, right? Now heat carried away by the dry products. What are the dry products? Carbon dioxide and sulfur dioxide, right? Nitrogen, say nitrogen is a part of air. So specific heat for nitrogen and oxygen will take as 1.005. This is specific heat for dry products, means carbon dioxide and sulfur dioxide mainly. So we will take only carbon dioxide and sulfur dioxide, MCP 1.0, how much? 045 into 327 minus 15, that is 945.5 kilojoules per kg. Heat carried away by the vapor, how much vapor is formed, how much hydrogen is formed? Hydrogen is 0.45. So vapor, heat carried away by the vapor, 0.45 into 3000 is equal to 1350 kilojoules per kg. Sorry, kilojoules. It is not kilojoules per kg, it is kilojoules. This is also kilojoules. This is also kilojoules. Right? Now heat carried away by the oxygen and nitrogen. Heat carried away by the oxygen and nitrogen is 12.172, right? Plus, what is the value of oxygen? Oxygen is, excess of oxygen is 1.21, 242, 2.42 divided by 2, it is 1.21. This is excess of oxygen, This will, and this mass mCp here will be 1.005 and delta T. All these values will be added, and then we will get the final heat which is going with the flue gases. In a nutshell, we will find the heat carried away by the flue gases. The flue gases consist of carbon dioxide, sulfur dioxide, nitrogen, oxygen and water vapor. So, heat carried away by the carbon dioxide and sulfur dioxide can be calculated by using this equation Q is equal to mCp delta T, where m is the sum of the mass of the carbon dioxide and mass of the sulfur dioxide. For both of them, the specific heat is 1.045 kilojoules per kg Kelvin. Tg is 327 degrees centigrade, that is the temperature of the flue gases, and Ta is the temperature, ambient temperature of ambience or ambient temperature. And this gives the heat transfer of dry product as 945.5 kilojoules. So, the second is heat carried away by water vapor, that is mass of the water vapor multiplied by the enthalpy of moisture. Enthalpy of moisture is given in the statement of the problem, and mass of the hydrogen oxide, that is water vapor, is 0.45, and this heat taken away by the vapor turns out to be 1350 kilojoules. Now, thirdly, we calculated the heat carried away by oxygen and nitrogen, and both of them are having the specific heat of 1.005 kilojoules per kg. So, we have taken the mass of the oxygen and the mass of the nitrogen multiplied by the specific heat, again multiplied by the temperature rise, and heat taken away by the oxygen and nitrogen is 4189.8 kilojoules. The sum of all these three values is 6486.3 kilojoules. The proportion of calorific value of the fuel which goes with the flue gases. So, this proportion of the calorific value of the fuel which goes to the flue gases is the ratio of heat with the flue gases divided by calorific value of the fuel, multiplied by the 100 will give the percentage of proportion of the calorific value going with the flue gases, and that is 21.6%. Right? That is all for today. Next time we will start with boiler trial.